So welcome back. Today we're gonna talk about the tyrosine kinase linked receptors. Here's some literature if you're interested in this topic. And we have an example here. We have the EGF, the epidermal growth factor receptor, which consists of two inactive receptors here. And each of these receptors have a tyrosine kinase domain. So whenever there is a dimer signal molecule, a ligand, activating those receptors, they bring them in direct neighborhood here, which leads to a cross-phosphorylation of the tyrosine domain of the receptors. So this receptor phosphorylates this domain and the other way around. The phosphorylated domains then act as docking sites for other proteins, which leads to a signal cascade inside the cell. Let's have a word on the ligand of EGF receptors. The EGF is released as a proform which sticks to the cell surface, and when the secreting cell decides to release the EGF, a protein is expressed called ADAM. And ADAM cuts the transmembrane domain here and sets the EGF free. The EGF receptors, on the other way, there are 4 known receptors. We call them HER1, HER2, HER3, and HER4, and it stands for human epidermal growth receptor. By the way, HER2 is an orphaned receptor. This means there are no ligand discovered yet which can bind to it, so it is always inactive in the normal cell. But sometimes a mutation in the genetic code of the receptor can lead to a constant activation of the receptor, which is then associated with a higher risk for breast cancer. When these receptors are activated, they activate signal pathways, which is called the MAP-Kinase-Signalpathway. How does this work? Well, the phosphorylated domains here lead to the recruitment of the GRB2 adapter protein. And the GRB2 recruits other proteins like SOS, which then recruits another protein, which leads to the activation of this MAP-Kinase pathway. Let's have some words on the different components here. Let's start with the GRB2. GRB2 has no enzymatic activity, but it connects functional enzymes to the receptor, which can be seen here. By using different adapter proteins, the cell can increase the specificity of the signal. And GRB2 consists of an SH2 domain for binding to the receptor, and then different SH3 domains, which is used as docking station for other proteins. The next protein we talk about is the GEF. GEF stands for guanine nucleotide exchange factors, and the GEFs bind to adapter proteins like the GRB2 and activate downstream kinases. An example for such an GEF is the SOS protein. And the GEF then forms a pocket when it binds on the GRB2, where a RAS kinase can bind. And normally RAS is bound to GDP, but with the help of the GEF, GDP is exchanged with GTP with the help of this SOS protein here. The way when it binds, the GDP is replaced, exchanged with a GTP, and the RAS is activated. And the mechanism of this GDP exchange is called a push and pull mechanism. RAS are molecular switches, which means that they are turned on or off by the phosphorylation of this GDP. The RAS superfamily has 4 subtypes: RAS itself, RHO, RHB, RHN. And RAS needs to be deactivated again, and this can happen via G protein activated proteins here. And RAS itself then activates the MAP-Kinase pathway, which is, in this case, it's the RH-Car pathway. It is named after the last kinases here. So in fact, it's just activating different kinases here, step by step, which phosphorylate other proteins or other kinases. And in the end, this leads to the activation of enzymes which start transcription or other cellular responses. These kinases here, they don't float in the cell. They are organized in a molecule which is called a kinase scaffolder, which is short for kinase suppressor of RAS, KSR1 here. And KSRs are actually not suppressing the kinases as the name might propose, but instead they are holding them all together and thus enhance their activity. The group of scientists who discovered KSR used too much of this molecule, and this led to a lower enzymatic activity because the MAP enzymes had been separated on too many KSR1 molecules. So this is the idle state, and this was performed by the scientists who discovered the scaffolders, which is why they are called suppressors. Instead, they are enhancers, and they are fine-tuners. How do we turn our MAP signaling off? When phosphatates can remove phosphates from activated kinases, we can have loops like the phosphorylated like enzymes that can phosphorylate our SOS enzyme leads to a lower affinity for the SOS to the binding site of GRB2. And we can, of course, always remove receptors from the cell surface. I hope this was informational for you. If any questions, just leave them in the comment. And I hope to see you again. Have a wonderful day.